In this lecture, we are going to explore the relationship between temperature and volume and essentially follow the work done by Jacques Charles, who is a French mathematician, scientist, and interestingly enough, a balloonist, as I recall, who basically did a lot of the initial measurements on a variety of gas samples, very careful measurements to explore the relationship between temperature and volume of a gas. All right, so let's go ahead and take a look at the type of temperature temperature and volume measurements that Charles looked at to put together the relationship that's now known as Charles' law. So the data here on the x-axis, what we're looking at is temperature, and I'm providing the temperature in two different scales. We're going to look at the Kelvin scale and Celsius. All right, and then what we're going to see is the change in volume in the y-axis as a function of that temperature. Okay, and the solid lines and the dots represent the regime in which data was collected. Okay, and so what we're looking at, let's go ahead and look first at this blue line. So the blue line is the result of individual measurements taking at different temperatures starting off at 0 degrees Celsius. So 0 degrees Celsius or 273 Kelvin, and then increasing the temperature, right, incrementally. And every one of these increments here represents a 100 Kelvin or 100 degrees Celsius increase. And what we can see from this data is that as you increase that temperature, the corresponding volume also increases. Right? And so this is something, again, that we can draw upon our common everyday experience to shed some light and to essentially validate. So, for example, if you take a basketball out of your garage first thing in the morning, throw it in the trunk of your car to play some basketball at lunch, and you notice as you're putting that basketball into the trunk of your car that it's a little flat, so you remind yourself, yeah, when I take this out at lunch, I'm going to have to pump it up before I go play. But then after your basketball's been sitting in the trunk during a hot summer day, when you take that basketball out of the trunk, you might find that it is actually fully pumped up. It feels fully pumped up because the temperature of those gas molecules inside of that basketball have increased and they start to occupy a larger volume, right? And so our basketball feels full. Okay, and so there are a variety of examples, and so this idea then that volume increases with increasing temperature isn't necessarily very surprising at all. Okay, and so what Charles did was then basically carry out these sorts of measurements, using these different temperature and volume readings, and then used different amounts of our given gases. So, for example, the blue line here represents gas samples that have taken a 1 atmosphere of pressure and 0.25 moles of the gas, and then carry out the same sort of measurements, right? For example, up here, looking at this purple line. So the purple line shows values that are again taken at 1 atmosphere pressure, but now the number of moles has been doubled. Okay, and so the key thing to notice here, of course, since the number of moles have been doubled, right, the gas is taking up more space, so the volumes are higher for the second line. But once again, all of these points, right, are falling along a nice straight line right here, the purple line. Okay, and lastly, if we double the number of moles again, bring it all the way up to a full mole of gas particles, of course, the volume is even higher now, but all of those given measurements are falling right along a line. Okay? And so just as we saw in our previous discussion of Boyle's law, what we're going to do is think of what sort of mathematical function best describes this relationship that we're seeing. Now, this one's not a terribly hard one to figure out. The relationship in this case between volume and temperature is going to be a simple linear relationship. We are going to see that volume is directly proportional to the temperature. Okay, and so the lines here are also pointing to some very important points. Right, once we come up with this line, this solid green line, using essentially a least squares fitting method. If we were doing this in practice, we can then extrapolate that line and see where that line is going to cross the y-axis. And it turns out that if we extrapolate all of these lines, we end up right down here at this absolute 0 point. Okay? Now, of course, we can't obtain that point experimentally, and in fact, the behavior of these gases, when you start going down into this lower region of temperatures right down here, these relationships start to break down. Yet, what we can find is that there is convergence here. Okay? And so remember how I said in the introductory lecture that it's going to be very important when we're developing these relationships that we use an absolute temperature scale. And so here's our first hint as to why that is. Right? So the absolute temperature scale gives us that kind of common point of convergence here for all three of these different data sets. Okay? So Charles's law put succinctly is given right up here at the top of the screen. Basically, we see a direct proportionality between temperature and volume. Okay, so let's go ahead and explore the ramifications of this direct proportionality. So remember, Charles' law, it's telling us temperature, volume are directly proportional. And so let's keep that in mind and take a look at the following example. Let's suppose we're given a system with some initial volume, we'll call that V1, and some initial temperature, T1. We're tasked with finding the final temperature, we'll call that T2, after a fourfold expansion of the gas. Okay? And as often the case with these problems, what we're going to do is make this assumption that the other thermodynamic parameters not listed, in this case pressure and amount, are held fixed, right? And so when we're setting this up, what we're going to do first is essentially write out what we're given. Well, we know there's going to be some initial temperature and initial volume, okay? Then there's going to be an expansion process that's carried out, and we are tasked with determining the final temperature. We're not going to know that one, given the fact that the gas expanded fourfold. So in other words, right, V2 here is going to be 4 times V1. Okay, so those are the given variables. Now what we're going to need is a relationship that allows us to relate these four variables, T1 V1 and T2 V2. Okay, so this relationship, of course, is going to come from Charles's law. We know from Charles's law that volume is directly proportional to temperature. So if volume is directly proportional to temperature, what that means is, that volume, if I divide by temperature over here, this ratio is always going to be a constant. All right. As a result, the ratio of V1 over T1 is going to be equal to the ratio of V2 over T2. And so our goal here is to solve for T2. So we need to solve for this variable that's down there in the denominator. So the first thing I'm going to do is move T2 up to the numerator by multiplying both sides by T2. All right? And then I'm going to isolate that variable T2 by multiplying both sides by the ratio T1 over V1. Okay? And then what I'm going to do is plug in the values that we know. We know that V2 is actually going to be equal to 4 times V1. So V1s are going to cancel out, and we will find that the final temperature is going to be 4 times the initial temperature. Okay. In other words, in order for that gas to expand fourfold, the temperature must increase fourfold, under the conditions of constant pressure and amount. Okay, so that's, again, that just goes back to our direct proportionality that we saw in the previous plot. Okay, now what I'd like to do now is go through another example, another quantitative example, and this example actually points out one of the very common errors that I see students make when you are looking at applications of Charles' law and doing some basic problem solving. Okay, so I'll make sure and draw that out. So first, let's read through the problem here. So in this problem, we're given a sample of gas, and we're told that the volume of that gas is 2.80 liters, and it's at some unknown temperature. Okay, so we don't know, right? But we know that when that sample is submerged in an ice water bath at 0 degrees Celsius, its volume decreases to 2.57 liters. Okay? So using that information, we now want to figure out what that initial temperature is. So writing out what we're wanting to find here, we have some initial condition here, which we don't know the temperature. That's going to be our goal, right? But we do know that the initial volume is 2.80 liters. And then we are submerging this system into an ice water bath that gives us a final temperature of 0.00 degrees Celsius and a final volume of 2.57 liters. Okay, so just as we did in the previous problem, what we're going to want to do is set up our relationship and solve for our unknown value of T1. So of course our relationship is going to be VI over TI equals VF over TF. And so then once again we are going to isolate that unknown variable, which is TI. Right? We want to solve for TI. So I'm going to move TI up to the right-hand side. And then I'm going to multiply both sides by TF over VF. Okay. All right. So then, once we have this relationship, what students are typically very excited to do is to go ahead and plug in your given values. Right? We're going to plug in the fact that we know the final temperature, final volume, and initial volume, and come up with some sort of solution. Okay. However, something happens here, and I've in fact designed this problem so that a little warning flag should come up if we try and do this directly. So I want you to think for a second, what would happen if we plugged in the given values directly into the equation as they are given? Okay, so you can pause the video, think about that for a second. Hopefully you will find that, well, we are plugging in a value of 0 degrees Celsius for our final temperature. And so what that would mean is that the initial temperature must be 0 degrees Celsius, which of course doesn't make any sense given the problem. Okay? And so when something like that happens, right, you should immediately think, oh, wait a minute, right? We are dealing with ideal gases, therefore we need to use our absolute temperature scale, our Kelvin temperature scale. Okay? So in reality, what we should have done is converted that temperature into Kelvin. And once we've converted the temperature into Kelvin, then we can plug in our expression directly. We can say, hey, we've got 273.15 Kelvin, and then we are going to divide by the final volume, 2.57 liters, multiply by the initial volume, 2.80 liters. Right, liters is going to cancel out, and we will be left with our final answer in Kelvin, which comes out to approximately 298 Kelvin. Okay, so once again, this makes sense, right? We are starting off at a larger volume, right? And we submerge this balloon at a temperature at 0 degrees Celsius or 273 Kelvin, right? And the volume decreases. Well, therefore, the initial temperature must have been higher, right? And of course, that's what the calculations show. So it looks like that balloon was sitting there roughly room temperature, and then you put it in your ice water bath. Okay, so here's the key problem. Once again, I want to remind you guys, we always need to be working in units of Kelvin for these ideal gas problems, right? This is going to be the number one area where students will miss points when they're solving problems for ideal gas, basic ideal gas problems. Make sure you're in a Kelvin system. In this case, I chose a value of 0 degrees Celsius to really force us to think about that Kelvin scale, right? Because we get a nonsensical answer, all right? But however, I could have been a little bit trickier and said, hey, what about maybe it was 5 degrees Celsius was the temperature of that bath, that cold bath. Okay, in that case, it would be very easy to just plug in that 5 degrees Celsius, get an answer, and move on with your day. Okay, and you wouldn't even realize that it is incorrect. Okay, so really important, can't stress this enough. You have to make sure that you transfer over to that Kelvin temperature scale for this ideal gas discussion. Okay, so to sum things up, we've basically developed Charles' law, which tells us that volume and temperature are directly proportional to one another, and it's giving us a nice little formula that allows us to solve basic problems where you are essentially given volumes, temperatures, right? Any 3 of these 4 variables illustrated here, and you have to solve for that unknown 4th variable. Okay, so that concludes our discussion of Charles's law. In the next video, we are now going to explore the relationship involving amount and volume. So amount and volume, and that's going to be the subject of Avogadro's law.